Welcome. We're back in college algebra, and today we're talking about solving linear equations. So we'll be describing what linear equations are, describing how to solve them, and we'll do quite a few examples. Let's begin today with where we ended last time. Last time we discussed the question of what is x? And we had several answers for that. If you'll remember, we really try to categorize x in three different ways depending on the context of the problem. The first way is sometimes we described x as an unknown, and in this situation, x is in an equation, and it just represents a space that there's a number that fits into it to make that equation true, and we're trying to figure out what number that is. And so x is just temporarily holding a spot, and we have to figure out what number goes in that spot. The next one was a yet to be defined number. And when we think of x as a yet to be defined number, we think of x kind of in a formula where we might have any number, any host of numbers being substituted for x once we get to that equation. So what we want to do is think of x as a number. It could be any number, we're not sure which one it is, but we want to manipulate it like it's a number. So we want to add with it, subtract with it, and that's where we do things like factoring and canceling just like we would with regular numbers. Finally, we think of x as a variable. And when we think of x as a variable, then we're really thinking of x in relationship with another variable. So we're thinking of all the different values that could be replaced for x, and then all the different outputs that might come, or all the different results that might come as a consequence of those values. And then we ask, how does changing x change the output, and things like that. So that's where we're going to get to for the richest part of this course, but today our focus is really on this top item, and that is x is an unknown. And so our goal is to come up with equations, especially equations which we'll call linear equations. And linear equations are for us, well, when you look at linear, you see that it starts with the word line. And so that might make you think of like a line that you would graph, and the answer is that that is what it is, and we're going to get back to that later in the semester when we describe graphs and shapes and the graphs that equations make. But for today, we're thinking of just the equation and just trying to solve with it. And so for us, linear equations are just equations that involve only multiplication and addition. So we're going to think of equations that involve only multiplication of addition. Now let me throw in that with an addition. Now let me throw in that when we add multiplication, we also add division to the discussion, and when we add addition, we also add subtraction to the discussion. I say that just because as a mathematician, I can sometimes be lazy, but to me, when I see the idea of multiplying and the idea of dividing, I really see the same idea but just looked at from two different angles. And the same with addition and subtraction. They're the same idea just looked at from two different angles. So these are equations that only have multiplication and addition. And I'll give you two examples real quick, and we'll talk about both these examples later on in the day. First example is the equation 3x minus 7 equals 4, and you'll see that we have a multiplication here with 3, we have a subtraction, and we have an equal sign, so it's an equation. Also, we have x plus 5 over 4 equals 3, and so we have an addition and a division, and so this fits as a linear equation. What I want you to notice is these equations don't have any sort of other things. They don't have like cubes or roots or logarithms or any of those things. These things are all taken off the table. These things are not for today's conversation. They will show up again in the very near future. So linear equations don't have those types of complicated elements. They only have elements that involve addition and multiplication. Now, let's start with an example. Let's start with the example x plus 5 equals 9. And my guess is that most of you can look at this and quickly see that the answer should be 4, because we all know 4 plus 5 is 9, and this is something that's very familiar with us. Something I'll do throughout the semester, and especially today, is we'll focus on things that seem very simple and seem very obvious, but the point is to understand these situations well so that when we get to the complicated problems that you'll get later on, that you'll be able to solve them as well. So let's focus not on what the answer is, but how can we reason our way to the answer. As I think about this problem, I think most of you would say we approach this problem by subtracting 5 from both sides, and that would be correct. We could subtract 5 from both sides, and when we subtract 5 from both sides over here, we get x, because this plus 5 and this minus 5 become 0, and then over here we get 4. So we get x equal to 4, which is the answer that we wanted. Okay, so again, we know the answer, but what we really want to focus on is the question, and the question is, why subtract? Why didn't we do something else to this problem? What was special about subtraction? And the answer is, we subtract because addition and multiplication, or addition and subtraction, are what we call inverse operations. So addition and subtraction are inverse operations. When you answer this question, you might have said something like, we subtract because they're opposites, or because the minus and the plus cancel each other out, or something. And the answer is, you're correct. That's what we mean by this phrase, inverse operations. What I mean by it is, I mean that if it's an inverse operation, it has the opposite effect. And so when I see this equation, I see that we started with x and we added 5 to it. So if we want x by itself, we have to do something that has the opposite effect. And the opposite effect is subtracting 5. And of course, we know with equations, for equations to remain balanced, we have to do the same thing on both the left and the right-hand side of the equation, which we did here. So there we go. That's just a little bit of thinking our way through this problem. Let's come look at another one, and we'll talk about a problem with multiplication involved. And so we have x plus 5, or 1.5x is equal to 9. So again, how might we approach this problem? My guess is that you're familiar enough to say that here we have a multiplication, and so to undo the multiplication, we need to divide. And so we will divide both sides by 1.5. If we divide both sides by 1.5, we get x, because 1.5 divided by 1.5 is 1, and that leaves just x by itself. And now we have to do 9 divided by 1.5. This might take a little bit of effort, but the answer is 6. If you're unfamiliar or feel uncomfortable doing this type of division, it might be worthwhile to go back and revisit my notes on multiplying and dividing with decimal places. Just click on the link below and it'll take you there. But again, let's ask the same question. Why divide? Why not do something else in this problem? And again, the same reason we divide is because multiplication and division are inverse operations. So we started with x multiplied by 1.5. We want to somehow undo that process. So what we need to do now is divide by 1.5. Let's move on to a problem that's a little bit more complicated. Let's move on to the problem 3x minus 7 equals 5. What you'll notice is that this problem has both a multiplication and a subtraction in it. So if you're thinking along with me, you'll know that we probably need an addition to undo the minus 7. We probably need a division to undo the 3. My guess is that if you have any questions on this problem, it's probably the question of what do we do first? Do we divide first, or do we add first? Here's how I think about it. I think of these problems first by using the order of operations to tell me what order do these numbers act on x. So if I look at this equation here, what do I see? What I see is that this x, the order of operations say you multiply first. So the first thing that happened was x was multiplied by 3. So x was first multiplied by 3. And then second, what happened to it? Second, it was subtracted by 7. So notice if we were to put some number in this equation, put say then any number in for x, you would multiply by 3 first and subtract by 7 second. So I put them in this order. Now the way I think about solving equations is when we do an equation, we always follow the opposite order. So we always undo in the opposite order from the way these terms acted on x to begin with. So we undo subtraction first, undo the subtraction first, and then undo your multiplication second. And this principle may seem somewhat simple, somewhat familiar in a problem like this, but in a moment we'll have problems that have multiple additions, multiple subtractions, multiple multiplications and divisions. And we have to think through which one do I do first and which one do I do second. And the answer is you always undo them in the opposite order in which they interact on x in this problem. So if I look at this, I want to undo my subtraction first. How do I undo subtraction? I undo subtraction by adding. And so I'm going to add 7 to both sides. And that gives me 3x is equal to 12. And then I undo multiplication. How do I undo multiplication? I undo it with division. So now I'm going to divide by 3 on both sides. And we get x equal to 4. And so there's our solution. Our solution is x equal to 4. And we did it by undoing your subtraction and your multiplication in the opposite order in which they interacted with x. Let's look at another problem that's somewhat similar. If I look at this problem, I might say, if I were to put a number in for x, what order would they interact? Well, I would say x first had added 5 to it, and then it was divided by 4. So if I want to undo these, I undo them in the opposite order from which they were added to the problem. So we undo our division first, and we undo our addition second. So what I always do is I always undo in the opposite order I'll write that down. So we always undo in the opposite order from which they interacted in the original problem. So if I were to look at this problem, I need to undo this 4, and so I'll do that by multiplying by 4. And I have to do it to both sides, so I'll multiply both sides by 4. This 4 and this 4, you could say they cancel each other out. What really happens is they divide to make the number 1. It behaves the same as canceling. So we get x plus 5 on the left, and on the right we have 12. And now we need to undo the 5. We undo addition by subtraction, and so we subtract on both sides, and so x is equal to 5. Oh, wait. I subtracted the wrong number. I should have subtracted 5, and x should equal 7. Okay, let this be a note that even your math teacher makes mistakes when they add and subtract. Finally, let's come to a problem that has several layers and has quite a bit going on, and see if we can work our way through it. It's the problem 3 times x minus 2 plus 7 over 5 plus 4 is equal to 3. So you see we have lots of things going on. We have a multiplication, a division, 2 additions, and a subtraction. And so the real question is, what order do we go through to undo these things? Which ones do we undo first, and then which ones wait till later? And the answer is you always undo in the opposite order from what we began. So I think of it kind of like an onion, and I'm going to put this little note up here. I always think of it as we go from the outside in. And you'll notice that we have an x, and then next to that x is a 2, and then nested next to that is a 3, and next to that is a 7, and next to that is a 5, next to that is a 4. So it's like this x has been nested inside all these other operations, and when I try to undo them, I'm going to work from the outside inward. I kind of compare this to the metaphor of peeling an onion. You have an onion and it has all these layers, and you peel off one layer at a time until eventually you get down to the very center, and the very center is the x. So we want to peel off one layer at a time. And when I look through these problems, what I see is I see the layers. So I see this as the most outside layer, so I'm going to undo this part first. And then I see this as my next layer, and so I'm going to undo this part second. Then I see this as my next layer, so I'm going to undo this third. This is my next layer, so I'll do this fourth, and then finally my last layer is the one that's right in here next to x, and so I'll undo that layer fifth. So if you're struggling with which operation you should do first when solving these equations, try to think of it as outside in. Outside not meant where they are in proximity, but where they are as in the order in which they've operated to x, the order in which they've interacted with x. So again, this one operated with x first, so it's the last thing that gets undone. This plus 4 is the last thing that's connected to x, so it's the first thing you take off. Okay, let's go through solving this problem, and we'll solve it one layer at a time. And so first, we'll do this first part, and that means we'll subtract 4 from both sides. And this will give us 3 x minus 2 plus 7 over 5. We had 3 and subtracted 4, so now we have a negative 1. Next, we need to get rid of this 5, so the 5 is now the outermost piece. And to get rid of this outermost piece, we need to multiply by 5. We multiply both by 5. These 5's undo each other, and we get 3 x minus 2 plus 7 is equal to negative 5. Notice you should have this 5 that you divided by cancel with the 5 you multiplied by. If they don't cancel, then you made a mistake, right? Because that's why we did the multiplication, for the express purpose of undoing this division. Okay, let's slide up and give ourselves a little bit more space. Once we're down to this problem, we can now subtract 7 from both sides. We get 3 x minus 2 is equal to negative 12. Our next step is to divide by 3. X minus 2 is equal to negative 4. And finally, we add 2 to both sides. And so x is equal to negative 2. And that solves our problem by going outside in. So we started with something that was quite complicated with a lot going on, but what I really want you to see, and this is the confidence I want you to develop in this course, is that you can start with things that look quite complicated, but if you just take them one piece at a time, just deal with one piece at a time, you can slowly chip away and work your way down to a problem until you end up with the solution that you want. Now, when we look at this problem, and we have this answer, there's a really big question we want to ask ourselves, and it's the question, how can I know if I'm right? How do I know if I got the right answer, or if I made a mistake somewhere along the line? And the answer is, you know it's the right answer if you can substitute back in for x, and x is the right number that gives you the correct solution to this problem. So let's come over here and look at this problem. And give me just a second to set up. So we'll notice that, how can I know I'm right? Well, the answer is, you know you're right if you have this equation, and we take our x that we just found. So we found our solution was x equals negative 2. And we want to take this negative 2 and we want to put it in for x, just like that. So our negative 2 gets replaced for x. And what should we hope our answer should be? Well, I'm going to put a question mark up here. If we did it all correct, our answer should be 3, just like the 3 that we found earlier. So if we put the negative 2 here, do a bunch of computation, just add and subtract and multiply as we know we're supposed to. If we get 3 out for our answer, then we know we did everything correct. So let's try this out and see how it works. So this gives us 3. Notice I have negative 2, and negative 2 gives us negative 4 plus 7 over 5 plus 4. Now if I take this piece, I'm going to put my 3 and my negative 4 together next, and that'll give us a negative 12 plus 7 divided by 5 plus 4. Now, my negative 12 plus 7 gives me negative 5 over 5 plus 4. Let's jump down to the next line. Negative 5 or negative 5 is negative 1 plus 4. Negative 1 plus 4 is 3, and I'm going to put a big check mark because that means we got the answer that we wanted to get. We placed our answer as. So negative 2 must be the right answer. 1, we did the work to find that it was the right answer. But 2, when we placed it back in our equation, everything calculated out correctly to give us the answer that we hoped we would get. If I'd placed my number in and gotten a number other than 3, then I know that I made a mistake somewhere, and that gives me a chance to go search all of my work and try to explore for the mistake. I know many of you, particularly students, don't find this process of checking for mistakes or exploring your work fun or exciting. And let me say, I've been a student before, and I found it that way also. But as a mathematician and a professor, I check my work on every single problem that I ever do, and it's just become a discipline and part of something that I always do. It started as a student because I didn't want to lose points on my quizzes and homeworks, and so I would always want to check and make sure I knew I was getting the right answer. But it continued even as a mature adult because I want to know that the answer that I'm getting is correct and not incorrect. Okay, I have one last task for you students, and the task is to try to solve 3 problems. And so I have 3 problems written out here. And these problems are an order of difficulty higher than what we've done so far, but they've solved the exact same, they use the exact same principles that we've used so far. So here we have x minus 1 divided by 2 plus 1 divided by 2 plus 3 equals 5. And how do you approach this? You have to, again, work outside in, just the way we've done so far. Here we have a linear equation, but we have a bunch of fractions involved. So we have 4/5, and then inside the parentheses 1/2 x minus 1/10 equal to 3/10. So you get to brush off some of your skills with working with fractions, and if you find that difficult, you can follow the link to my video about working with fractions. Finally, on the last section, we have a similar problem, except this one involves decimals. And so we have 0.02x minus 1.2 over 2.5 equals 1.4. So what I would like you to do right now is I would like you to take your device, whether you're on your phone or on a computer or on a tablet, and pause it and take 4 or 5 minutes, maybe even longer, and try to solve these problems and really invest yourself into doing them correct before you wait and see if you got the right answer. So hit pause now, and I'll give you just a minute. Okay, so we're back. You've now unpaused your device, and you're ready to see the answers. These are the answers I got when I solved the problem. I think they're correct because I checked them. And I got x equal to 7 for the first problem, x equals 19 over 20, and x equals 23.5. If you would like a more detailed solution for these problems, I have links connected over here. So click on those links, and it'll take you to a page where I detail the solution. Thank you all very much. Come back with us next time, and we'll talk about how to solve equations that go beyond linear, that have some of these other elements like squares, roots, or logarithms that we talked about earlier. Thank you.